Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 8.2 by having a small discussion about infinite solids. The idea of this discussion is, again, to get a little bit more practice with some of the geometric ideas that we've discussed in our class, namely volumes and surface areas of solids of revolution, but also to tie that into sort of the broad concept of our entire class, which is infinite behaviors. In this class, we've discussed a lot about convergence and divergence and what happens when you sum up an infinite amount of infinitesimally small things. And since we are getting sort of close to the end of our course, I'd like to sort of put together a lot of those concepts, both the geometry and this idea of accumulation, and investigate a little bit about sort of a theoretical part of geometry, which is the idea of infinite solids or infinite shapes. So, in this video, we're going to discuss two questions, and we're going to see if if there are actually shapes or solids that have the sort of descriptions that we're going to be talking about here. So we have two questions here. We want to know, is it possible to have a shape that has infinite surface area and finite volume? And our second question is it possible to have a shape that has finite surface area and infinite volume? Now, you'll notice that we're not bothering to ask a question like, is it possible to have a shape that has a finite surface area and finite volume? That's pretty much every shape you've ever encountered in your life, right? They have a finite surface area. They're made out of a finite amount of material or whatever, and they have a finite volume. They can only fit a finite amount of stuff inside of whatever that shape is. So finite surface area, finite volume, that's pretty much everything out there. We might not encounter many things, but infinite surface area and infinite volume, also obvious, right? You just take a cylinder that is infinitely large. That's going to have an infinite volume and an infinite surface area. What we're interested in these two questions is it possible for one of the geometric quantities to be infinite, but the other one be finite? So infinite surface area and finite volume, finite surface area and infinite volume. And we're going to tackle both of these questions sort of separately. It turns out that one of these two situations is possible. There are shapes that satisfy one of these two questions, and the other one is impossible, meaning that no shape exists that has that particular pair of traits. You might think a little bit about which situation is which. Do you think it's possible to have infinite surface area and finite volume, and finite surface area and infinite volume? So one of those combinations is possible, one is impossible. Before we get into sort of investigating this mathematically, I'd also like to give you guys just a little bit of sort of a common sense approach to deducing which of these two is possible and which is not. If you think about it, this first one is saying that you have an infinite surface area and a finite volume. Infinite surface area means that it takes an infinite amount of stuff to build the shape. But finite volume means that you can only fit a finite amount of stuff inside of it. Now, that doesn't sound like it's very easy to do, but if you think about it, that's basically just saying that you build your shape in a really, really dumb or inefficient manner. You build it so that it takes an infinite amount of material, but it only holds a finite amount of stuff. So it seems like perhaps this is possible if we construct something that is basically built very, very poorly. If you use the same sort of logic on this second one saying it takes a finite amount of material, but it can fit an infinite amount of stuff inside of it. Now, if you think about that one you should be very skeptical about. And the reason you should be very skeptical about it is that if this was possible, if it was possible to build something with a finite amount of material and an infinite volume, we would build it immediately. That would be something which we could construct, at least theoretically, and then throw an infinite amount of things into, and it would never fill up. That would be incredibly useful. And since we haven't built it, it stands to reason that it probably can't exist. Not that it doesn't exist, but it simply cannot exist. So what we are actually going to do in this video is we are going to give an example of this first one. We're going to actually show and build a shape that has an infinite surface area and a finite volume. And we are going to prove this is impossible. So we're going to do two things here. We're going to give an example to show you guys that it is possible to have infinite surface area and finite volume, and we're going to actually formally prove that it is impossible to have a finite surface area and an infinite volume. And that will sort of answer the questions about infinite solids. So let's start off by taking a look at our example here. All right, what we're going to do is we're going to consider the solid created by revolving the curve y equals 1 over x for x greater than or equal to 1 around the x-axis. So we want to know what is the volume and surface area of this solid. So what we're going to be doing is we're going to be taking our sort of curve here. So we'll go 1, and of course this would be 1, 1. That's where our curve will start, and it'll be 1 over x, so it's going to go like that. It's going to have that horizontal asymptote, so this is y equals 1 over x. We're taking the area under this curve and above the x-axis as standard. Didn't say that in here, but we're just going to assume that that's the area that we're going to be interested in. And we're going to go ahead and revolve that around the x-axis. So the shape that we would build, here's the sort of mirror image of it. It would look something like that. And it would sort of have sort of a horn type shape with this long infinite extension down this way. And notice that this is certainly an infinite solid because we're doing this for x greater than or equal to 1. So we're not stopping at any particular value. We're just going from 1 onwards. So let's talk about the volume and surface area of this. So let's go ahead and investigate the volume first. Now, since everything's in terms of x, let's go ahead and do this with respect to x. So, since we have a horizontal axis, this implies that dis and washers will allow us to do this dx. So, if we want to work dx, we can use dis and washers. So, let's draw ourselves a little typical disk here. It shouldn't be too bad. We draw perpendicular to our axis, and there we go. Notice that it is going to be a disk here. It's not going to be a washer, just a normal disk. So what is this volume going to look like then? Well, it's going to be the integral. We're going to start from 1. We're going to go all the way out to infinity. Then pi. And our radius is going to be our function. And then squared dx. So that would be an expression for the volume of this infinite solid. Now, we don't know if this volume is finite or infinite or whatever. We just know that that's the integral expression for the volume of this solid. What type of integral is this? Well, we called this a type 1 improper integral. Notice that this also gives us a way to sort of review back to what we were doing back in improper integrals at the end of chapter 7. So what was our sort of general approach for dealing with an improper integral? Well, we always changed it into a limit of a definite integral, making use of a sort of dummy variable. And we've got this as 1 over x squared dx if we simplify a little bit. And now we can sort of focus on how to actually evaluate this. Shouldn't be too hard to do. We have the limit as t goes to infinity, integral 1 to t. We can think about this as pi x to the minus 2 dx. Then we can go ahead and integrate this. If we integrate this here, we should have our limit as t goes to infinity. If we integrate this, we add 1 to the exponent, we're going to get negative 1, divide by that, and we get negative pi x to the minus 1, evaluated from 1 to t. And let's plug that stuff in there. And we're going to get negative pi over t minus pi over minus negative pi over 1 when we plug in the 1. So we should get that the volume is the limit as t goes to infinity minus pi over t plus pi. Okay, now we can determine if it converges or diverges. This limit as t goes to infinity causes this to go to 0. So we get that our volume is equal to pi. So this converges. So this shape has a finite volume. So what does this sort of mean then? Well, if it has a finite volume, what we're really saying is we're saying that if you were standing here at, I guess, this end of this giant shape, and you started to pour stuff into the into this horn or into the shape or whatever, well, after you poured a pi amount of whatever sort of liquid or whatever you're pouring in there, this shape, despite being infinitely large, would start to spill out, right? Stuff would start to spill out because it would have filled up completely. It only has a finite volume. So we just constructed an infinite shape that has a finite volume. Now, let's investigate its surface area. So let's go ahead and we'll talk about its surface area. So we'll keep the same sort of diagram. So there's our 1, 1. There's our curve going this way. And if we look at this thing, There's f of x, or y equals 1 over x. And again, we're revolving around the x-axis, so there's our mirror image. And we have, again, this sort of horn shape. So we want to investigate its surface area. So we have surface area around x-axis. So we know the sort of general formula is going to be the integral 2 pi y times the arc length. We probably still want to go ahead and work dx, so we can go ahead and do that. That means our surface area here is going to be the integral from 1 to infinity, 2 pi. Instead of y, we're going to have to replace that with the function, which is 1 over x. And for the arc length, well, if we have y equals 1 over x, which of course is x to the minus 1, then we can think about dy dx as negative x to the minus 2, or if we prefer, negative 1 over x squared. So the arc length would be the square root 1 plus negative 1 over x squared dx. And if we simplify that, we now have that the surface area is the integral from 1 to infinity, 2 pi, 1 over x, square root, 1 plus 1 over x to the 4th dx. So there we have an expression for the surface area of this infinite shape. Now, if we wanted to go ahead and try to evaluate this, we'd have to change it into the limit as t goes to infinity, integral 1 t, just like we did beforehand. But I'm a little hesitant about doing that because this looks pretty messy to do. If I try to do some sort of u sub, like 1 plus 1 over x to the 4th, then the du is going to be like a negative 4x to the minus 5, which we have nothing like around. So doing a u sub would be very, very challenging. This in here is not like a 1 plus u squared for a trig sub. This is a very challenging integral to actually try to do. So instead, we're going to use a sort of trick that we've talked about back in improper integrals. We're actually going to do a comparison test. What we're going to do is we're going to note that square root 1 plus 1 over x to the 4th is always strictly greater than 1. Why is that? Well, if you look at this, 1 plus 1 over x to the 4th, well, if x, no matter what x is, this is going to be always positive. So this is always 1 plus a slightly positive number, which means it's always slightly greater than 1. So this is always greater than 1. So what does that tell us? Well, that tells us that 2 pi 1 over x root 1 plus 1 over x to the 4th is always greater than just 2 pi 1 over x. Right? If this thing is always a little bit greater than 1, then multiplying by this is greater than just having this original term. In other words, multiplying by this makes this thing a little bit bigger than that. But what do we know about this? Well, if we think about the integral from 1 to infinity of 2 pi 1 over x dx, that, of course, is just 2 pi integral 1 to infinity 1 over x dx. And if you think back to what we learned about way back when we first did improper integrals, type 1 improper integrals, we had something called the p-test, which said that if this power was greater than 1, then this integral would diverge. So this, we know, this diverges by p-test. But what did we just show here? We just showed that the function we're integrating, right, our function right here, is greater than this thing that diverges. So when you're greater than something that diverges, you also diverge by comparison test. So we can say by comparison test, integral 1 to infinity 2 pi 1 over x root 1 plus 1 over x to the 4th dx also diverges. So what did our example show us then? Well, what this tells us is this shape, we'll summarize here. So just a quick summary, since we did two things. Summary, this shape has finite volume and infinite surface area. So, in other words, the shape that we were just discussing, if we go back to sort of our first page, this sort of giant horn shape would take an infinite amount of material to build, yet it would be fillable by a finite amount of stuff. And in fact, we know that finite amount, it would be fillable by pi units of whatever sort of thing you could pour into this. Now, this is actually a very famous sort of shape. This is called Gabriel's horn. That's why I keep referencing it as a horn shape there, because it is sort of a known construction in mathematics called Gabriel's horn, after the archangel Gabriel, who's supposed to ring in the end of days. And if you're ringing in the end of days, most likely you would use an infinitely long horn. So that sort of seems to make sense. So this is a really famous shape because the idea is that it shows us that if we build something sort of really, really inefficiently, really poorly, in other words, you can use an infinite amount of material, yet it'll only contain a finite volume. So, in other words, we've answered that very first question. Is it possible to have a shape that has infinite surface area and finite volume? Yes, it is. We just built one. Are there other examples? Sure, there are tons and tons of other shapes you could build that have infinite surface areas and finite volumes. But I wanted you guys to see at least one situation, one actual construction of that, which we use this, sorry about that, well, having a little bit of trouble there, this Gabriel's horn there. What's also interesting about this Gabriel's horn is that it is based around that function that we have seen so many times, that 1 over x. Remember back when we were discussing series, the sum 1 over n was the harmonic series. It's a really, really sort of important fundamental structure. It was the first example we saw of a series whose terms go to 0, but the series still diverges. So it's a really nice example that if you use the corresponding function, 1 over x, you can build this shape that has finite volume and infinite surface area. Also, good in terms of just a review here to remind you how to actually approach a improper integral of type 1, and also a clever use of comparison tests to avoid actually having to deal with calculating the surface area. So we simply compared it against a known divergent improper integral. Okay, now let's change gears a little bit and actually prove that that second question can't happen. Remember, our second statement was, is it possible to reverse this and have a finite surface area and infinite volume? And we're going to prove that that's impossible. So our last thing we want to do here is we're going to prove that if the volume is infinite, then automatically the surface area will be. So in other words, if you want to have the ability to put an infinite amount of stuff inside of it, then you need an infinite amount of material to build it. So we're going to prove this. So this is sort of an interesting one, again, because it's always nice to see some more examples of proofs. This is also a great example of a sort of proof because the statement of it in words is very simple. If the volume is infinite, then the surface area is infinite. But we really got to sort of figure out what that sort of means mathematically. So let's give ourselves a sort of situation here. Let's assume we have some sort of function like this. Now, again, we don't know what that function is. So I'm going to assume that it starts from some a. And we're just going to call this y equals f of x. And we're going to assume that it goes around the x-axis. You're going to also notice that with my assumption here, we're going to be assuming that the limit of f of x as it goes to infinity does go to 0. If the function didn't go to 0, if it did something like that or went up like that, then there is no doubt that this volume and surface area will be infinite because everything's just going to get larger and larger. What the situation we're always interested in is what happens if it gets really, really small. Is it then possible to have this finite volume, infinite surface area, all these different questions? So we're going to just make a little note here that we're going to assume that the limit as x goes to infinity of f of x is equal to 0. Now, we're also going to assume the volume is infinite, and we need to show that the surface area is infinite. So let's see if we can write down an expression for the volume. So again, we're going to be imagining that we are taking this area here, and we're going to be revolving it around the x-axis like this. So again, to do the volume, we can sort of set up the volume just like we did before. It's going to be an integral. We'll say a to infinity this time, just because we're going to start it from some arbitrary value. Pi, if we're doing discs and washers, again, the sort of example disk is going to come around and be something like that, just like the other one, except now we don't know what this function is, so we have to do it sort of abstractly. So it's going to be pi f of x squared dx. And so, since this is an expression for the volume based on discs and washers, we're going to assume that this is infinity. So this expression diverges. So we get to assume this. We get to assume that this volume expression here diverges. And we need to show that the surface area is infinite. So we get to assume this here. All right, let's go ahead then and talk about what the surface area is. Well, the surface area would be the integral from a to infinity, 2 pi. And if we use the same sort of expression, we would say we'd want to use y, but we have to replace that with f of x, and then square root. Well, 1 plus, we could say dy dx, but we might as well just say f prime of x squared dx. Okay, so there's our surface area expression. Now again, we don't get to assume what the function is because we're trying to prove this in general. So we're going to try to use something like comparison tests so that we don't actually have to compute anything, because it would be impossible to compute things here because we don't actually have the function. So there should be no doubt that 2 pi f of x root 1 plus f prime of x squared is strictly greater than 2 pi f of x. Why is that? Well, again, same trick. This here is something squared, so this is always going to be positive. 1 plus something positive is always a little bit greater than 1. So this is 2 pi f of x times something that is a little bit greater than 1. So this is a little bit greater than just 2 pi f of x times 1. So that should be very clear. And certainly, it should be clear that that is greater than pi f of x. Now, we want to compare this surface area to this thing here that diverges. This thing here has pi f of x squared. Now, can we say that pi f of x is greater than pi f of x squared? Well, not necessarily, because if you square things, squaring things sometimes makes them larger and sometimes makes them smaller. If you square something like 3, you get a larger number, 9. If you square something like 1/2, you get a smaller number, 1/4. So we can't necessarily just say this is greater than pi f of x squared. But we can say that based on our other assumption. Remember at the beginning, we took the time to mention, if we go back up here, that the limit as x goes to infinity of f of x equals 0. In other words, f of x is getting smaller and smaller. So if f of x is getting smaller and smaller, at some point f of x goes below 1 and stays below 1. Why is that important? Well, when you square numbers that are smaller than 1, they get even smaller. So what we can do is we can say that this is greater than pi f of x squared. And we can make this assumption here once f of x is less than 1, which must happen for some x greater than or equal to, let's call it b. So it won't necessarily happen for a for a little while, but at some point at b, our function will dip below 1 and stay below 1. How do I know it has to stay below 1? Because the limit is approaching 0. So if you're headed to 0, you have to get below 1, and then you have to stay below 1. So in other words, we can make this assumption as long as we're looking a little bit beyond our initial starting value. Now you might say, well, does that work if we start at a? Well, of course, because remember, when you're talking about infinite things, you only care about the long-term behavior. So the fact that this comparison test doesn't work from a to b doesn't matter, because it does work from b to infinity. And that's what's going to determine the convergence or divergence. So this is totally fine, even though it only works maybe after the first few values and then onwards. So what we've shown is our surface area here, this expression, is strictly greater than this. Well, since we know that that volume expression diverges, we know by comparison test the surface area diverges. So by comparison test, since the volume approaches positive infinity, so does the surface area. So in other words, this shows you guys that it is impossible to have something that has an infinite volume and finite surface area. And we've proven that if you have an infinite volume, you automatically have an infinite surface area. So this sort of concludes our discussion of infinite solids. Again, this is not a main part of this section 8.2. 8.2 is really just trying to get you guys to understand how to measure surface areas of finite shapes. But since we had spent so much time earlier in our course talking about improper integrals and talking about convergence and divergence, I do think this is a nice sort of tie-in, just getting this idea of thinking about these sort of theoretical infinite solids. If you're curious, you can actually investigate these constructs at a lower level. We sort of did everything here 3D, so we were talking about volumes and surface areas. You can also investigate this in 2D, where the equivalent to volume would be area, and the equivalent to surface area would be something like length or perimeter. So it turns out that the same sort of results hold. You can build a shape that has an infinite perimeter, but a finite area. A famous example of that is sometimes called the Koch snowflake. It's a fractal shape, and if you want, you can research it. It's a pretty interesting little shape there. And you can prove that the opposite is impossible. In other words, you can prove that if you have a shape that has infinite area, it automatically must have an infinite perimeter. So that's sort of the lower level version of the results that we just talked about here. For now, though, this wraps up Chapter 8, which sort of ends our discussion of these geometric constructs that are measurable through definite integrals. In our next video, we'll be moving into our last chapter, which is Chapter 10, starting with looking at parametric functions.